Hello again and welcome. Today we're going to be assembling a kit. I'm sure you CB and amateur radio guys will recognize this fairly quickly. This kit is used to build an RF transformer. So a while back on the EV blog, somebody had posted about building a 9-to-1 un. They were having troubles with the assembly, and so I got involved. I started winding up some transformers for the fun of it. So when I was looking online, there's a lot of videos where people are winding up these transformers, but rarely have I seen anybody actually test them. They go so far as to put the coil into the box, and that's about as far as they get with it. So I thought what we'd do today is build this one up, and then we'll go ahead and test it out. So it looks like it comes with a fair amount of wire and some gasketing, your connector, a couple of screw terminals, the box, which is all pre-drilled, and of course the core. So I purchased this kit off of Amazon. It's sold by AE Creative. You can see this kit is advertised to work for 160 meters on up to 10 meters. It comes with a T200-2 Type 2 iron powder ferrite core, all hardware to build your own balun or un up to 1.5 kilowatts to make a 1-to-1, a 4-to-1, or a 9-to-1 balun or un as desired. We don't provide any plans. The optimum resonant frequency range is 0 to 40 megahertz. That's pretty impressive if it's true. As far as how to wind the transformer, you can see this one's showing the exact same core, 9-to-1 un design. So under construction, he says the triple bifilar windings of 10 turns are wound evenly spaced around the T200-2 powdered iron core. And this is basically how the core gets wound. So again, you have a trifilar winding, 10 turns. Now let's go ahead and get started. First thing we need to do is unspool our wire. So then I'm just going to fold this thing over to basically give us 3 equal lengths of wire. I'm just going to pull on these to basically get them straightened out, take any kind of kinks out of them. That looks pretty good. Alright, let's have a look at our core. So again, we're just going to keep these 3 pieces of wire fairly close to one another. We'll leave enough on this side to be able to terminate the transformer. Now we're just going to start wrapping this thing through. Again, we want to keep the wires fairly tight. We want to prevent putting any kinks into the wire. And we don't want them to cross over. Again, I just pull them tight. And we'll just stitch it back through. Actually, for this video, what I was hoping to do was just purchase a pre-wound un. That way I'd have some kind of idea that the core was assembled right and it had been tested. So I had asked the amateur radio group if they'd recommend a transformer, but nobody had any recommendations. So, and I figure with the original poster building their own transformer, why not? We might as well wind one up. Again, we're counting the number of turns through the center of the core. So 1, 2, 3, 4, 5 so far. We're about halfway through. We could start in the middle of the winding. I figured for 10 turns. We'll just start at the end. Not a big deal. Right there you can see how they're trying to cross over. We want to avoid that. You can see they supplied more than enough wire for this particular design. I mean, you can see there's 10 turns. I probably got an extra 2 feet of wire or so. I think what I'm going to do, I'm just going to back this out 1 turn, and then I'm going to go ahead and add a couple more turns. I know his document said 10 turns, but I can't add more turns without rewinding the core, but it's fairly easy to take them off. So we're going to start off with 12 turns. And you can see, even if I cut the wire up here, that gives us plenty to work with. There we have it. So we're going to put these in series, so we're going to attach these 2 wires together, and then these 2 wires together. This will become our 450 ohm source, and this will become our ground down here. And again, because we're going to be probably removing more turns, I'm not going to permanently attach these together. So to get the insulation off, I'm just going to use an X-Acto knife. You can use sandpaper. I just drag the knife blade. So again, I don't want to drag it this way and cut into the wire. I'm just dragging the blade across the insulation. And we're going to do the same for this wire. Again, the manufacturer's claiming this transformer can be used up to basically 30 megahertz and down below 2 megahertz. So fairly low frequency. As far as tinning the wire, we're going to be using a fairly large tip. And we'll just go ahead and tin these 2 wires. Fairly tin for the most part. Looks like we missed a little spot right here. We'll just come back in, clean that up a little better. That looks pretty good. And we'll do the same with our second wire here. Like so. And we just attach these 2 together. Now again, I'm anticipating we're going to be changing the number of turns. So I'm not permanently going to attach these 2 wires. We're just going to tack the 2 together. Like so. And now we have to repeat this process for the next 2 windings in the chain, which will be these 2. Now keep in mind that these are going to be our input, so these will go back to this connector here to the center post. So again, to give you some idea, if we place the transformer in the box like this, we don't need a lot of wire. Only something like about this here. And we'll just snip that off. And again, we'll just go ahead and scrape off the enamel. And we tin these 2 wires the same as the other 2. And we can just temporarily attach the 2 together. Alright, again, because this is a 9-to-1 transformer, your radio is going to be typically 50 ohms on its output. So this will be our 50 ohm unbalanced input. The output impedance is going to be 9 times 50 or 450 ohms. So unfortunately, I don't have a 450 ohm resistor, but I have this one here, which is 470 ohms. And you can see basically 466 ohms. Good enough for what we're trying to do here. So the next step is to attach this between the output and ground. Alright, the next thing we're going to do is attach a small SMA connector. I'll just be using a small piece of rigid, and we'll just start by attaching our center conductor. like so, and then we'll attach our ground wire, and we also need to attach our 470 ohm resistor. Again, not real critical at this point. And we'll just attach our output to the other side of the resistor. Like so. And now we're ready to give it a try. You can see we have our light VNA out. And we'll go ahead and link and sweep. And we'll load up a calibration. We'll select old and calibration, and we'll select 400K to 4 megahertz. And we'll attach our cord to port 1. Let's have a look at the SWR. It's not very good. So down here at 1 megahertz, you can see we're about 30 to 1 SWR. Even up at 3 megahertz, it's not very good. Let's try sweeping it up a little bit higher. Again, we'll select 2-port cal, old, and let's do the 1.8 to the 29.7. It definitely has a sweet spot. You can see it about 12.5 megahertz. If we move our cursor up to 1.8 megahertz, you can see the SWR is 7.84 to 1. Let's just try it at 30 megahertz, and you can see it's 2.64 to 1. So not very good. Let's go ahead and we'll store this to memory 1. Again, we'll just pull 1 turn off for now. Clip our wires to roughly the same length again. Take our needle nose and we'll just straighten these up. And again, scrape the insulation off. Again, I want to be very clear. I am not a radio hobbyist. I don't own a CB. I have an old Drake transceiver. It's vacuum tube type, but I have no license to operate it. I did when I was a kid. I would say ham radio was my stepping stone into becoming a professional engineer. Had a lot of fun with the hobby back in those days. I couldn't tell you anything about what the organizations do today, CB or ham radio. I just don't have any interest in either of them. So my interest here is really just winding up these transformers. And I thought it'd be kind of a, like I say, interesting video if we actually ran some tests. It's just not something I was noticing on the various videos I was watching. And again, we just tin all 3 of these wires. And we'll reattach them. Again, this is not the final configuration, so I'm not too concerned what this looks like just yet. And we'll reattach our SMA connector. And we're ready for round 2. Let's go ahead and reattach our transformer. Looks like our SWR now at 1.8 is gone up to 9.72, and at 29 megahertz it's gone down a little bit to 2.5. But again, even at 3 megahertz, let's have a look. I would expect the amateur radio guys would be using something like this for the 80 meter band. And here we can see at 3.7 megahertz we still have an SWR of 3.4 to 1, so not very good. We pull off another turn, it's just going to hurt that performance even more, but we'll gain a little bit on the high side. Let's see what it is in the 40 meter band, so somewhere around 7 megahertz. So 7.17 megahertz, it's 1.6 to 1. Looks like the sweet spot here is basically 12.5 megahertz, and the SWR is perfect right there at 1.0 to 1. I think what we're going to do is just follow our friend's instructions, and we'll pull one more turnoff. So basically we're going to replicate his design. So you can start to see a theme as we trial and error this. Try to spread these out a little bit further. Just try to keep our coil spacing somewhat even. And because this is our final configuration, let's go ahead and we'll cut these a little shorter. So again, we want these two to overlay roughly like this. Just pull a little bit off of here. So to terminate these two wires together, I just got a small piece of Teflon tubing here. I'll slide that over the top of these after I've soldered them together. Then we're just going to tack these two together for right now. I'm going to take a piece of 30 gauge solid core and we'll peel the insulation off of this like so. Now I'm going to loop this around our two wires here to give it some mechanical stability. Get this thing to lay a little bit flat like so. Then we'll just go ahead and solder these two together permanently. We'll take our Teflon now and push that over the top of our solder joint like so. Alright, looks good. And again, we're going to go ahead and shorten these up a little bit, assuming this is our last try. So I'm going to basically bring these into the center, straighten some of the kinks out of this one. Again, it's easy to take the wire off, but difficult to put it back on, so that's the reason that we're making these measurements. So again, we scrape off the insulation. You can use sandpaper for this. I've done that as well. They make a product called an eraser, which is almost like a grinding wheel. There's a very soft compound wheels in there, and it basically strips the wires. We used to use that for very fine wires that were like 40 gauge. Just kind of feed it in there and it pulls the insulation right off. Works really good if you've got high temp insulation. And again, we'll go ahead and tin these two. And again, I'm just going to use a piece of this 30 gauge to stabilize this joint. And we'll kind of bend this around. Looks pretty good. And again, we'll solder these two together. And again, we'll go ahead and attach our SMA connector. Like so. And we'll trim our ground wire. And again, more scraping. And again, we tin it and attach it to the shield of our coax. Again, you can see we now have 10 turns. This is going to be our final configuration. Let's go ahead and hook this up to the network analyzer and see how this has affected the performance. And we'll just attach it to port 1. And we can see the performance at the lower bands now is much worse. It's 13:1 at 1.8 megahertz. Not very good at all. Again, we'd expect this to be somewhere around 2:1 and less. Let's have a look at our highest frequency. You can see we didn't gain much, so SWR is roughly 2.46 or so to 1. I'm saying this is not a very good transformer. Not for the amateur bands anyway. Let's have a look at that web page again. I think he shows some data for his core. And look, so very similar. SWR would be in red, and you'll notice again at the lower frequency this thing goes off the map, and he tested all the way up to 31 megahertz it looks like, and he's seeing a SWR of roughly 3:1 at 31 megahertz. So this would be 3 megahertz here. He's at roughly 5:1. How does that compare again to ours? At 3 megahertz, we're at like 4:1 and 2.46. So our transformer is actually a little bit better than what he's showing on his web page. Does he say that this is a bad core choice? So let's see, he's got a conclusion here. This on should be useful from 7 megahertz to 30 megahertz, and at a push on 3.5 megahertz if nothing better is available. Yeah, I don't know. Again, I'd say we'd like to see 2:1. Let's just turn off that memory. So at 2:1, we're at 6.6 megahertz, and on the other side, we're at 26 megahertz. So yeah, I would say somewhere between 6.6 and 26 megahertz. You're below 2:1 SWR. Of course, again, we don't have a 450 ohm resistor here. This measurement's going to be off just a little bit. So let's see what we have here for hardware. So they would like you, it looks like, to mount the connector in from the outside like this instead of through. Yeah, I'm almost wondering about running those wires underneath the core instead over the top. So maybe I have one terminal here and then one on the top side here. I think that's what we're going to do. I think to do that, what I'd like to do maybe is put a little Teflon over this wire. Same thing as our output. Let me get a piece of that. So this is a small section of coax. I'm actually thinking what I'm going to do is use the braid off of this coax for our ground. So we need about this length total. And all I'm going to do is pull out the center core. We need about this much here. We'll just go ahead and trim a section of this off. Maybe about here. Trim a little of that off. And here's our ground strap. Looks like they give you some ring terminals. We'll go ahead and attach one of those. We'll just solder this together. So it looks like you get a couple of locking washers and then these tabs and these nuts to secure these. Let's just open up our braid here a little bit, like so. And just kind of slide this over our post here. And then we'll go ahead and solder this whole assembly together. And that'll become our ground. Again, we just put a lock washer on, and then our nut And we'll just go ahead and tighten this up a bit. That's good. And we'll just kind of line this and snug it down a little bit. You know, I'm not a fan of just putting this nut over the top of this. What I'm going to do is go ahead and add some star washers to this. Alright, let's just go ahead and we'll tighten up these first two. Next we'll just go ahead and remove the shield out of the inside of this other section of coax. And again, we're going to be using that sleeve for the output of our transformer. And I think what I'm going to do is again run this through the bottom. Have tempted to shave these down a little bit further though. We're definitely crowding the top of the case. So let's go ahead and do that. And again, we retin the wires. And again, we'll loop the two of these together. Again, we'll just trim the excess here. And we'll go ahead and solder this together. That's much better. Alright. Maybe just bend the terminal 90 degrees like so. Set the core in and then tighten down our ring terminal. Seems like it'll work fine. Go ahead and add our last screw. Again, we got this huge long terminal here. I'm thinking for this, we just go through like this and bend it flat. Basically just loop it around and crush it. Good enough. And we insert our lock washer and our second nut. It gets a little sloppy up in here, but I don't think that's going to be any kind of a problem. Let's go back to the network analyzer and have a look at it. Before we do that, we have to come up with a new load. So these are some old ohmite resistor. This is a carbon comp, 470 ohms. Went through these and I found one that was a little low. You can see 463 ohms or so, and we're looking for 450. Probably tight enough. What we could do is go ahead and install the gasket as well. Again, this just press fits into the cover like so. Because this transformer is never going to get used, I'm not too concerned about it. There you go. Again, normally this would just fit together like so, and then we can insert our 4 screws. But I've got some additional tests that I'd like to run with this before we do that. So let's go ahead and we'll attach our resistor. Now let's head back to our network analyzer. Because this isn't a connector I would normally use, I purchased a couple of adapters. And these came off of Amazon. So these go to an N style. We're going to go from this N to the SMA. And again, we'll go ahead and attach our light VNA to the transformer. This is where we were at 26 megahertz. It's a little lower, it's 1.9 to 1 now. So we could bump that up a little bit to get to 2 to 1. So right there, we're at 2 to 1 at 27 megahertz. See on the bottom end, we're at 2.03. And again, that's at 6.6 megahertz. But again, I think a lot of the amateur radio people that would be using something like this probably want it for the 160 and the 80 meter bands, maybe the 40 meter. I don't see the CB guys using something like this. The next thing what we want to do is go ahead and power this thing up. So the RF generator is set for 30 megahertz. This is a good range for our CB friends. So here you can have our fluke meter out. The reason we're going to be using this instead of the BM869S is because I've tried these experiments before with other transformers, and I'm finding that this Bryman meter is actually sensitive to the RF. So I had put some ferrite on the thermocouples, and that seems to tame it, but at the higher levels of RF, I couldn't get the meter to behave. This particular fluke meter so far has been immune to all the testing that I've done. Again, here we have our transformer and our 470 ohm resistor attached to the output of it. And I have a BNC to N style connector. Here I have my little SWR meter that I had when I was a kid. It's made by Mars. It's a model SW50. See on the back, we can select it for 52 or 75 ohms. You can see it's set for 50 ohms on both the in and the out. And then I have a couple of adapters to get me down to B and C. We're just going to put this right in line with our transformer. And then to drive this, we've got this little amplifier here. This is using a MRF 453. This is currently set up for 30 megahertz. You can see it's just a single pill, I guess is what the CB guys call them. They call these transistors pills. I don't know. So we can get a couple of watts out of this thing. Let's go ahead and we'll attach this to our meter. And we'll attach our signal generator to the input of the RF amp. Let's have a look with our SWR meter. And you can see it's just a little over 1.5 to 1. The resistor's starting to heat up a little bit. So I've applied a little bit of thermal grease to our thermocouple. See if we can get that to give us a better idea how hot that's getting. Alright, let's go ahead and turn it back up. Now let's see what our core temps are like. And I'd expect this thing to be very cold. Oh yeah, I can't feel any heat in that core at all. Of course, we're not putting out a lot of power right now, just a couple of watts. Again, this is a 2 watt resistor. So at least for CB use, I think you're probably okay using this. Let's try it at some higher powers. So I'd mentioned that I'd ran some similar tests. So I had built a few transformers before this. This is one of them. There's a couple of 1206 resistors on the back side. These are making my 450 ohm resistor. Again, it's a common ground plane. This is a un as well. I don't remember which core I used on this particular one. I tried to get a little bit wider frequency response and ended up with this one. Worked fairly well. So then I decided to start building some bigger ones. This is one of my attempts. And then I went to a 2-core system. That's this one here. It's actually 2 toroids taped together on each side. And you can see I've made a load for this one. These are all 470 ohms. There's 16 of them stuck together. Again at 2 watts a piece. This transformer works fairly well. I decided to build something with a little bit higher power. That's this transformer here. Now this has 8 different cores stacked together on both sides. Again, this is a un. Here's the 450 ohm side versus our 50 ohm side here. So then I went back to a single core. This actually works really well. The frequency response for these two are much better than what you get with this transformer. These will both work well down into the 160 meter band. Of course, as I was building these, I was testing at higher power levels. You can imagine starting out with something like this and ending up with something like this. So what I started doing was testing these back to back. So one of these I attached to my 50 ohm load, and then I drive the power into the other side. So I had my two thermocouples attached to both of these cores. This transformer here basically stays ice cold. This one I took up, I don't remember how high, but it got so hot this Kapton tape was starting to smell and it was delaminating. So I thought, geez, I wonder what the amateur radio guys are using. So again, this thing is rated for 1.5 kilowatts. You can see the cores physically a little bit larger, a lot more turns, again 10 turns versus my 5 turns on this. This is a TDK HF90 material, if you're interested in looking that up. Again, frequency response on this is very good, but it's not going to be good for very high power. So what I'm thinking to do is we'll attach these two together in series. Again, the SWR for this one is very good compared to this. It won't add a whole lot of error to the measurement, but I'm just kind of curious, if we put a little bit of power through this, is this core going to start to heat up? Again, what I'm going to do is have this drive into a 50 ohm load, and we'll have our power amplifier attached to the front end of this. So normally what I'm going to do is I'm going to hook this up to my watt meter. I've had this for quite a while. This is made by ProTech. It's a model 2700. I don't think they sell this anymore. You can see it's rated for 500 milliwatts continuous, no damage. Now I think the specs on this thing are 10%. It's not very good for accuracy. Let me just see here. Accuracy plus or minus 10% of full scale for 10 megahertz to 1 gigahertz. So 10% of 500 milliwatts is going to be 50 milliwatts. Of course, what we need to do is attach an attenuator between the input of this meter and the output of our transformer. So we can't use anything like this. This isn't going to handle the amount of power. So I have some larger attenuators. You can see this one's rated for 2 watts. This is an old JFW attenuator I purchased, used on eBay. Of course, it was non-functional. Imagine that. So the attenuator had burned up. I don't know, they overloaded it. Anyway, so I got some parts from Barry. The part that's in there is actually rated for 150 watts, and that's assuming that the heatsink temperature stays below 100 degrees Celsius. If it gets any hotter than that, it's going to derate. Now you can see I've added these 2 fans. These are to cool the attenuator. Unfortunately, for testing these Ballons, that's not going to be enough, because I think that the amateur radio guys are limited to 200 watts if they got their basic license. So it seems like we need to test it at least 200 watts. So a little bit too small for that. So we're going to need a larger attenuator. And again, the watt meter is only good for 500 milliwatts. So normally what I would do is follow this with a 10 dB attenuator, giving us 30 dB total. So this 100 watts is going to provide 100 milliwatts on the output. So we're going to leave these attenuators off, and we're going to attach this to a larger 10 dB attenuator. So here's our test setup. You can see I have my 2 Fluke 189s. They each have a thermocouple attached to them. Thermocouple goes to each of the 2 transformers. Here I have our little cheapo power meter. This is attached to the output of this 20 dB attenuator. And then on the front side of that attenuator, we have another power attenuator. It's a little bit bigger. This is rated for 300 watts. This will easily handle the 200 watts that the amateur guys can run, or the CB guys. And you can see I've just got my thermocouples attached to the two transformers. I guess if you're curious what this whole arrangement looks like, let's just do a quick measurement of that. And so you can see I have our light VNA out. It's attached to the input of this transformer, again in series with our other transformer in the back, to our two attenuators in series, and again connected to our power meter here. And if we look at the SWR at 30 megahertz, you can see it's now 2.4, so very acceptable, I guess, for this test. So yeah, so adding all this really hasn't affected the SWR of our transformer. Again, compared to our 460 ohm resistor, this is of course going to handle a lot more power than what we're able to handle with this for a load. So this is looking at my watt meter, and the far left we're looking at forward power, reflected power in VSWR. I have a cross needle meter in the center, and then I also display the forward and reflected power in dBm, and then I can graph that below. I'll just show you down here. This is looking at the average, and I guess you'd call this the peak power. Let me just adjust the amplifier a little bit, give you an idea how fast this will track. So fairly responsive. So what I'm going to be doing next is we'll take the power and start turning this up a little bit while we're monitoring the temperature of the two cores, and let's just see what happens. Alright, so ideally we'd like both of these cores to remain cool. Let's go ahead and start turning this thing up a little bit. Almost forgot, you guys like bird watt meters. There we go. That's a little better. Now let's start turning up the power. I don't know if you can see this, but our little watt meter, well, when it's laying flat it's about 235. Now it's displaying about 250 or so as I'm picking it up. Now it's down to about 230. I'll just show you. Get the camera off here. See, about 220. See as I'm lifting it up. Yes, the power of watt meters. The other thing you can see, negative 35 degrees. Our meter's having a little bit of problem. It looks like with the RF on that core. Let me see if I can attach it to the winding. Now, as soon as I bring it near it, it's having an issue. Let me get a piece of ferrite out. Like I said, I was able to tame the Bryman meter with a little bit of ferrite. Maybe we'll get lucky here. Alright, there we go. Not too bad. Again, we're well within the rating of this attenuator. I'm thinking we crank this thing up a little further. Again, that transformer that I made out of that TDK HF90 material, that would have been well over 100 degrees C right now. Let's bring a little fan here. Try to cool that down a little bit. Alright, I just cut the power on the amplifier. And let's see. Is there a hotter spot on this core? And this is down towards the center. Not too bad. I mean, it's not cold. But again, looking at the transformer we just built, yeah, 45. Again, it's cooling down. $49. Again, we're only putting out a few hundred watts. Or birds, I guess. That's what the CB guys call them. You got a 200 birds you're putting out. And she's definitely a little on the warm side. And again, same meter looking at our core. A little cooler. I don't know if this thing would actually handle 1.5 kilowatts. I'm kind of doubting it. I think I'd like to see it. Maybe it's just my poor construction practices. Anyway, I think that's going to be it for this video. Hope you enjoyed it. It's not, again, something that you're going to see me using in the future, but just thought you might find it interesting. Well, that's all for now. Oh, shoot, there is one other thing. For the few of you who voted, I've received our new meter. This is a Keysight. This is the higher end one. I had tried to get the 1281, and I couldn't find it in stock anywhere. So you can see this is actually what we received, is the 1282A. So we'll be running this in a future video. Nice looking meter. Again, I've done a video where I've looked at the front end of this before. We modeled it up on some circuit board and I kind of went through the design. My question on this, first of all, would be, what's that rotary switch look like? It'll be very interesting to see if we find another glass-filled detent spring in here. Well, that's going to be it for now. Again, till the next video, stay safe and we'll see you then.